In this video, we will look at the idea that electric and magnetic fields can store energy. We'll start with looking at the energy stored in a capacitor. We know the expression is UC equals 1/2 Q delta V, but using the relation Q equals C delta V, we can rewrite that in a couple of different ways. 1/2 Q squared over C and 1/2 C delta V squared. Using this version and the knowledge that for a parallel plate capacitor, the capacitance is epsilon naught A over D, and that the electric field in a parallel plate capacitor is nice and uniform, we can also say that delta V equals ED. And so using these two ingredients, let's rewrite the energy. So I've replaced the C with epsilon naught A over D, and I've replaced the delta V squared with ED squared. And this is just the magnitude of delta V, so I have the magnitude of the uniform field E and the distance D between the plates. A is the area of one of the plates. All right, I can simplify this expression. What I'll do is, so I canceled one of the D's, I gathered the A and D together, and then the remaining factors are 1/2 epsilon naught times E squared. But if we think of this as energy stored in the electric field, well, in a parallel plate capacitor, where you have, say, two plates, each of area A, separated by a distance D, we know that the electric field is non-zero only between the plates and is zero outside. So really what we have is a volume, right, enclosed by the, well, not enclosed, but between the plates, a volume between the plates where there is electric field and thus where there is energy. And since the electric field is uniform there, presumably the energy density is uniform. So we can think of this total energy stored in the capacitor as being a volume times an energy density. So that's exactly what our next step is. We'll say that the energy density in electric fields is this total energy UC divided by the volume where the energy is stored, which would simply be the area A times the distance D. So we get UC over AD. And so if we plug in our expression for UC, we get that the energy density, which is this little u with the subscript E for electric, this electric field energy density is 1/2 epsilon naught E squared. What about magnetic fields? Well, similarly, we start with the energy stored in an inductor, which is U sub L, which is 1/2 Li squared. And just as we had Q equals C delta V, for an inductor, we have phi B, the magnetic flux, is equal to L times I, where L is the inductance and I is the current running through the inductor. All right, so using that relation, we can rewrite UL as 1/2 phi B times I, or go one step further and write UL as 1 over 2L times phi B squared. But for an inductor with the shape of a solenoid with area of cross-section A cross and n turns in total over a length little l, we can say that the total flux through that inductor is the B field times the area of cross-section times the number of turns, because the number of turns basically multiplies the area. So B times N times A cross will give us the magnetic flux. And if we want, we can write that capital N, the number of turns, in terms of little n, the number of turns per unit length, times the length. All right. So our expression for UL, which was 1 over 2 L times phi B squared, becomes 1 over 2L times this expression squared. But in a previous video, we showed that for a solenoid-shaped inductor, L was mu naught little n squared L times A cross. So plugging that in, we get this expression for UL. And of course, there are a bunch of factors we can cancel. And what we are left with is L times A cross times 1 over 2 mu naught B squared. But of course, L times A cross is again simply the volume of the inductor, right? It's the area of cross-section of the inductor times its length. That is the volume inside the inductor. And that is where we have a nice uniform B field if our inductor is solenoid shaped. So once again, calculating the energy density, but this time for a magnetic field, we have UL over the volume, which is UL over L times A cross, and that becomes 1/2 B squared over mu naught.